Good morning. Hope everybody had a good weekend. So if you haven't seen already, I did get the test graded. So your grade should be posted. Just like the first test, if you just go into your grade book, click on the test grade, that should open up your submission. And in the column, right-hand column there, you should be able to see all of my feedback with correct answers and stuff. If you have any questions about that, please do let me know. Like I've told you before, feel free to email me with questions, or if you want to stop in during student hours, that's a great time to ask questions about your tests. And just keep in mind, right, the best way to study for the final exam is going to be to go back through those tests. We'll also have a final exam review in addition to that, but looking through those problems from the test will be a great way to study for that final exam. So just make sure you understand any mistakes you made so that you can correct those before the final. The other thing, don't forget the homework on sections 3.1 to 3.3. I did change that due date to tomorrow at midnight. So just make sure that you're working on that. We'll definitely get through section 3.3 today. And so I've moved that to tomorrow. The next homework will be due on Thursday right now. Again, we'll play that by ear, move the due date as needed. But for right now, that one's going to be due Thursday. And then I move the last homework for this chapter to Monday of next week. So you've at least got the weekend before that one's going to be due. Test is probably going to be sometime next week. I don't know exactly when yet, because we still got a few sections here to get through. But just know that my goal is to kind of finish up hopefully by early next week, which would mean that the test would probably be posted early, due in the middle of the week, late end of the week at the very latest for that next test, though. Okay. I think that's all I've got in terms of announcements. So any questions, comments, concerns before we get started? All right, as always, if you've got questions on homework, go ahead and send me those questions using the Ask My Teacher button. I'll be happy to respond to those. And if it's something that needs a little bit more work, then I can definitely work it out and email you pictures of my responses there too. Okay. All right, so jumping back here into section 3.2, we've got a couple more examples to finish up in this section before we move on to 3.3. Mean value theorem is what we ended with last week. Okay, so I just wanted to go back to this slide just to remind you of the formula for our mean value theorem. Remember what mean value theorem tells us is if our function is continuous on a closed interval and differentiable on the open interval, then we know that somewhere along that interval, there's going to be a point where the tangent line is going to have the same slope as the slope between our starting and ending points. Okay, and so that's what the pictures down there at the bottom show us. So what that means is there's going to be some value c where the derivative at that value is going to be equal to the slope between those 2 points, right? So that's what this formula gives us now. So if we can calculate the slope between the starting and ending point, we know somewhere in between there, there's going to be a tangent line that has that exact same slope, somewhere where the derivative is the same. All right, we did example 3, so let's take a look at example 4 now. We're going to use our mean value theorem to find a speed that a car must have traveled at least once if it went 180 kilometers over 2 hours. All right, so based off the information that's given here, what do you think we might want to do first? And thinking about the fact that we're going to want to use mean value theorem to figure out our answer. All right, so let's start here. Can we sketch a graph of this scenario? So think about what we would need on our graph if we were going to sketch this. So what would our axes have to look like? Okay, good. So we're going to have distance and time, right? In this case, I'll have my distance is going to be my vertical, and then we'll let time be the horizontal. So anytime you've got time as one of your variables, always let that be the horizontal axis. All right, now let's think about this situation. Where are we going to start on this graph then? At 0, right? So in this case, we've traveled 0 kilometers at 0 hours. So I'm going to start right here at the origin. Now, where else are we going to have a point on our graph now? All right, so at 2 hours, so if we go out, and I'm going to call this 1, 2, so here's 2 hours. We know the distance is going to be 180 kilometers. So I'm going to put 180 right up here. And so at 180, because this is our distance in kilometers now, we know there's going to be a point on our graph. Okay, and Anna, you just sent me a message. I just opened up the course content folder. Sorry about that. So yeah, chapter 3 slides should be available to anybody that wants to view them now. Let me know if you still don't see it. Okay. All right, so now we know we're starting at 0, 0, 0 kilometers at 0 hours. We know after 2 hours, we've gone 180 kilometers. So now the question we're trying to answer is, what's the speed that you would have had to travel at least once along the way if that's what you did? How are we going to figure that out? Okay, so we're going to use mean value theorem, right? All right, and Hector says we're going to find the slope, and that's exactly right, because in this case, we don't know exactly what's happening in between 0 and 2, right? This graph could be just a straight line like this from 0 to 2. It could also be that, we travel, a pretty long distance over and then we level out, and then we travel. But what do we know is for sure going to be true about this graph? If we start at 0, 0, we end at 2, 180, what's going to be true about this graph no matter what? Okay, I agree, right? It is going to be increasing, and it could be constant at some points, right? So if you look right in here, if you happen to stop for a while and not travel, along a certain time interval, it could flatten out. Okay, but overall, it is going to be increasing, right? What else is true about this graph? Think about our criteria for mean value theorem. It is continuous, right? So no matter what, okay, it doesn't matter how I connect these 2 points, there's never going to be any holes, there's never going to be any asymptotes. This graph is always going to be continuous. Now, the other thing that has to be true is it has to be differentiable, meaning I can always find the derivative. Is there any way I could connect those 2 points where I wouldn't be able to find the derivative between the 2 points at every point in between? So no matter how I connect those 2 points, right, and make this a continuous graph, I should always be able to differentiate it also, right? Because time is going to flow no matter what, right? There's no way that I can ever put a vertical tangent in there because time is going to continue no matter what I do with my distance. Even if I stop, it's just going to become horizontal, okay? But there's no way I can stop time. So it's always going to be continuous. It's always going to be differentiable, which means I can use mean value theorem. Now, mean value theorem tells us then that somewhere along the way, there has to be a point where the slope is going to be equal to the slope between the starting and ending point. Well, what would the slope represent in this case? Okay, it's going to be kilometers per hour, right? It's your distance over your time. So in this case, that's kilometers per hour, which is a what? A measure of what? Kilometer, not distance, right? Kilometers would be measuring your distance. Kilometers per hour would actually be a speed, right? Just like miles per hour would be a speed. So this right here is a speed. So when we're finding our slope this time, kilometers per hour, it's going to actually give us the speed between 2 points. Well, if I can find the speed, then the average speed between the starting and ending point, I know there's a speed somewhere along the way that's going to be the same because that slope at some point along there, right? Let's say that I connect these 2 points directly and I get a line that looks something like this. I can find another point somewhere on there where that slope is going to be exactly the same, right? And there's at least one place, which means there's somewhere along the way where the speed is going to be the same as the average speed between your starting and ending points. Any questions about that? Now, how am I going to find my slope then between my starting and ending point? Okay, so what do we know? What can we plug in here? All right, so it's going to be, in this case, 180 minus 0, technically, right? Because we're subtracting the y values over, and then we do the difference in the x value. So that's going to be 2 minus 0. That just becomes 180 over 2, which is what? 90. Good. So our average speed along the entire trip now is going to be 90. What are the units? Good. Kilometers per hour, which means that somewhere along the way, we have to have traveled 90 kilometers per hour. Now, we're not saying we traveled that the entire time. We could have, right? It could be a nice straight line between the starting and ending points. Okay. But generally, along a trip, you're going to speed up, you're going to slow down. Okay. But because the average speed along that trip is 90 kilometers per hour, at some point along the way, we had to have traveled 90 kilometers per hour. Any questions on that one now? All right. Example 5. So suppose that f of 0 is negative 3 and f prime of x is less than or equal to 5 for all of our x values. We want to know how large could f of 2 possibly be? All right, so we are going to use our mean value theorem here. So let's think about the formula for mean value theorem first. So f prime of c is going to be equal to f of b minus f of a over b minus a, where a is your starting point, b is your ending point, and we're calculating the slope now between the starting and ending point. We know there's going to be somewhere along the way where the derivative is equal to that slope. Now let's think about the information that we know in this case. So what's one thing that we know? Okay, so we're given that f of 0 equals -3. So what information does that give us that we can actually use in our mean value theorem now? All right, so it does give us a point, right? Think about what we need. All right, so it's either going to represent an f of b value or it's going to represent an f of a value. So let's figure out now which one is it going to be. Well, if it's f of 0 equals -3, and we know we're trying to figure out how large f of 2 could be, would f of 0 represent our f of a value or the f of b value? It's going to have to be a, because if you think about it, that means that our 0 here is the a value, and the b value is going to be what? 2, right? So we're basically looking now along an interval from 0 to 2, because a always has to be the smaller value of your x values, where 0 is a and 2 is your b value. All right, so now let's actually substitute into our formula to think about what we've got here then. Well, f of b is going to be f of 2, which we don't know, right? That's what we're actually trying to find, minus f of a is going to be f of 0, so what's that going to be? -3, right? So we're subtracting -3 over, and then b minus a is going to be what? 2 minus 0. Perfect, right? So 2 is our b, 0 is our a, so we just get 2 minus 0 down there. All right, now, what are we going to use for f prime of c this time? Exactly, right? We know that f prime of x is always less than or equal to 5. So that's the largest possible f prime value that we could see, which means that's also going to give us the largest possible f of 2 value that we could have. So if I just substitute 5 in here now for our derivative, when we solve for f of 2, that'll be the largest possible f of 2 value, and that's what we're trying to figure out. Okay, so it's going to be f of 2 minus a -3 just becomes +3. And then this is just going to be over 2 now. Now we just need to solve for f of 2. So what can we do at that point? Good. Multiply by the 2. So now we have 10 equals f of 2 plus 3. Then we subtract the 3. So now we have 7 equals f of 2. So this is our answer. So the largest possible value for f of 2 would be 7, okay, because that would give us the largest possible f prime value we could have, which would be 5 in this case. Any questions about how we did that one now? And just make sure you know your mean value theorem formula, right? But again, it is just slope. So if you just remember that f prime of c is equal to the slope between the starting and ending points, that's all you're really calculating there. All right, and then a couple of theorems here at the end. If f prime of x is equal to 0 for all x in an interval from a to b, then f is going to be a constant along that interval, right? So basically, if your derivative is always 0, that means your tangent line is always horizontal, which means that along that interval, the function just has to be a constant, right? It's always going to be a horizontal line there. Now, a corollary that comes from that theorem is that if f prime of x and g prime of x are equal to each other for all the x in some interval, it should be then f minus g is going to be constant on that same interval from a to b. Okay? In other words, f of x is going to be equal to the g function plus some constant. And so if you think about it this way, let me sketch a graph to kind of give you a picture of what we're looking at here. Let's say that I have some f function, right? And it doesn't really matter what it looks like along some interval from a to b. What this is telling us now is that if the derivative of f of x, so this is my f, and the derivative of g of x are always the same, they're always equal along that interval, that means the slopes of the tangent lines have to be the same everywhere, which means the basic shape of that graph has to be the same, but it doesn't necessarily have to be exactly the same graph, because it could be that we've taken the entire graph and just shifted it somewhere. Okay. I tried my best to match that to the bottom one, okay? But in this case, if you look at the bottom graph and you look at the top graph, as long as their shape is exactly the same and one is just a translation of the other, the derivatives along the way are still going to be the same because the slopes of the tangent lines at every point in that interval should be the same for both of those graphs now. Okay. Now, the reason this is important, okay, that f of x is equal to g of x plus c whenever those derivatives are equal, eventually we're going to start working backwards to where we're given a derivative and we're asked to find the original function. The original function in those cases is going to have this constant because we don't know exactly where it's going to land, right? All we know for sure is what the derivatives are equal to, but we don't know where it is in space because it could be way up somewhere or it could be way down somewhere. So we're going to have to remember to have that constant in our solutions when we work backwards, okay? All right, so that's it for that section. Now we're going to move on to section 3.3. This is where we're going to use our derivatives to help us figure out some things we know about our graphs. All right, so how derivatives affect shape of graph. Again, section 3.3. All right, so the first test we're going to look at is what's called the increasing decreasing test. So if our derivative, f prime of x, is greater than 0 on an interval, then f has to be increasing along that interval. So in other words, if the slope of your tangent lines is positive, then we know it's increasing, right? And you can see that on the graph below. Everything between a and b now, the slopes of those tangent lines would be positive. Therefore, this interval here would be an increasing interval. And on the other hand, if f prime of x is less than 0, if our derivative is negative, then we know the function has to be decreasing along that interval. So right here from b to c, Notice the slopes of those tangent lines would always be negative. Therefore, we have a decreasing interval. And then down here from C to D, again, the slopes of our tangent lines become positive again, and that interval is now increasing. So what we're going to be doing now is actually taking our derivative, figuring out first where it's equal to 0, and then we can do some tests to figure out, well, where is it positive, where is it negative, and that's going to tell us where the graph then is increasing and where it's decreasing. Any questions about what's on this slide now? Again, the main thing here, positive derivative, increasing graph, negative derivative, decreasing graph. That's what you need to know. All right, so we want to figure out where this function now is increasing and where is it decreasing. All right, so what's the first thing we're going to have to do here? We need the derivative. Good, right? So we're trying to figure out where's the derivative positive, where is it negative, so we can use our power rule now to find the derivative. We do that, f prime of x. Okay, I'm just going to go through this. 4 times 3 gives us 12, and then x to the third if we drop the exponent by 1. Next term here, 4 times 3 is going to give us 12 again. Drop the exponent by 1, that's x squared. Then we have 12 times 2, that's going to be a minus 24. This becomes x to the first power. And then remember, the derivative of a constant is 0, so the 5 just goes away. Any questions about that derivative? All right, now that we have the derivative, what are we going to do with it? Good. We need to figure out where it's equal to 0 because those could be those turning points, right? The critical numbers of our graph. And then we can look around those points to figure out where is it positive and negative. So I'm going to set this equal to 0 now. And so if we set it equal to 0, what are we going to want to do with the right-hand side? Factor. Good. So how are we going to factor this one? Good. We can bring out a 12x because that's our common factor. So take that out first. That's going to leave us here with x squared, then a minus x, and a minus 2. And always look to see if you can factor further. Okay, so if we look at what's left in the parentheses here, how would that factor? Good. X minus 2 and x plus 1. All right, now that we've factored it completely, what are we going to do next? Good. Set each of those factors equal to 0 to find those critical numbers. So 12x equals 0, x minus 2 equals 0, or x plus 1 equals 0. And so what are the 3 solutions we're going to get from this then? Good. This one gives us 0 when we divide by 12. Here, if we add the 2, we get positive 2. And if we subtract 1, we should get negative 1. Okay, so again, these right here are called the critical numbers of our graph. So So since that's where the derivative is equal to 0, there could be mins or maxes there, right? We're not guaranteed to have that, but those are the places we would want to check because there could be some turning points there, right? Now, what we're going to do with these critical numbers at this point is we're going to do a number line and we're going to test values around those critical numbers to figure out where the graph is positive and negative, where the derivative is positive and negative, so we can figure out where the graph is increasing and decreasing. Okay, so my next step now, draw your number line. Make sure you put your values in order here. So -1 is the smallest, 0 is next, and then 2 would be up here. And this number line represents our derivative f prime. So that's where we're testing. All right, so we got 4 different intervals that we've got to test now to figure out, is it positive or is it negative? So let's start down here on the left. What's a value in that first interval that we could test? -2 works, right? So I'm going to test -2. Again, make sure this is the first derivative that we're substituting into. So I'm going to plug in. Probably the easiest place to do that is going to be in the factored form right here, because all I care about is whether this comes out positive or negative. I'm going to have f prime of -2 is going to be 12 times -2 times -2 minus 2 times -2 plus 1. And if you can do this in your head without actually writing out the steps, that's perfectly fine, right? Okay, it's just I'm writing it out so we know exactly where we're substituting into. So 12 times -2 now, again, all I care about is the sign. Is that product going to come out as a positive or a negative value? It's -2. That's going to be negative, right? So this is negative. Then we're going to multiply that by -2 times -2. Is that negative or positive? Negative also, good. And then down here, -2 1, is that going to be negative or positive? That's negative. And so overall, if I multiply 3 negative values together, it should be negative, right? So this is going to be a negative in that interval. And you can also just plug into your calculator, right? If you want to go back to the original function, plug in a -2 and just see if you get a positive or a negative. But again, all we care about is the sign of that, right? Not the actual value. All right, now we need something in the next interval. So between -1 and 0, what's the value I could plug in there? A -0.5 works. So again, I'm looking at f prime of -0.5. It's going to be 12 times -0.5. Then we have -0.5 minus 2 and -0.5 plus 1. Okay, so again, now I just want to look at my signs for each one of those. 12 times -0.5, positive or negative? That one's going to be negative. Good. -0.5 minus 2. Also negative. And -0.5 plus 1. That's going to be a positive. Good. Now, if I multiply 2 negatives and a positive, that should give us what? That's going to be positive, right? Because remember, anytime you have an even number of negatives, that should come out as a positive value. This is actually going to be positive now. Any questions on that one? All right, so keep going. Between 0 and 2 now, what's the value of the test? 1 works. So again, we're looking for f prime of 1. It's going to be 12 times 1, 1 minus 2, 1 plus 1. And all I care about are the signs. 12 times 1, positive or negative? Good, positive. 1 minus 2 is negative, and 1 plus 1 is positive. This time we have 1 negative, which means the overall product is going to be negative. Good. odd number of negatives. 1 is an odd number, therefore it's going to be negative overall. And then finally, we need a value in that last interval. So what could we test there? 3 works. So f prime of 3, 12 times 3, 3 minus 2, and 3 plus 1. In this case, all 3 of these should be what? Positive, right? So 12 times 3 is positive, 3 minus 2 also positive, and 3 plus 1 is positive. Overall, then, that has to be positive. Good. Now, the one thing I will caution you on, it's very easy to get in a lull and just assume they're going to all alternate, right? Because we started with negative and went to positive, back to negative, back to positive. That's not always the case, okay? So be sure to actually test and don't just assume that they're going to alternate signs like that. Any questions up to that point, finding the signs for each one of our intervals? Okay. Now, I'll write my answer down here so I don't have to erase the work over there. So now what we're really trying to find is where is this thing increasing and where is it decreasing? So again, if we have a positive first derivative, then we have an increasing interval. And if we have a negative first derivative, then we have a decreasing interval. So what's one interval where this thing would be increasing? Good. From -1 to 0, we know it's increasing because we have a positive value there. Okay, so this interval right here is going to be increasing. And so it's just going to be parentheses, -1 to 0 parentheses. Your increasing, decreasing intervals should always involve parentheses because at those critical numbers, right, those are those turning points. And so we don't need a bracket there, right, because it's not actually increasing or decreasing at those critical numbers. Is there anywhere else where we're going to be increasing now? Good. From 2 all the way to infinity now. Okay, so be careful. Not just 2 to 3. This thing goes on forever to the right. Okay, so just make sure that you're including every value that's greater than 2. So I'm going to put a union symbol here, and then from 2 to positive infinity. Okay. And another common mistake I see is people accidentally use the test numbers that they chose instead of the actual critical numbers. Okay, so the number on the number line is 2, so it's from 2 to infinity. Okay, so make sure you're not starting with the 3, even though that's the point that we plugged in. Any questions about finding those positive increasing intervals now? All right, now we need our decreasing intervals. So what's one of our decreasing intervals going to be? Good. Negative infinity up to -1. Because that's the first place we have a negative, so that's decreasing. And then the other interval that's negative is from 0 to 2. So we have a union, 0 to 2. That interval is going to be decreasing. And so this is our answer now. Any questions on any of the work for that one? Okay, now, always a good idea to check, right? If you have access to Desmos, you might as well go ahead and graph it and make sure that your intervals make sense. So let's take a look at our graph in Desmos now. Okay, so this time we had 3x to the 4th minus 4x to the 3rd minus 12x squared plus 5. So I'm just going to bump my y-axis down a little bit so can see that bottom point. Go. All right, so based off what we got here, okay, I'm going to go ahead and these points where it turns. So we said everything from negative infinity up to -1 should have been a decreasing interval because we had a negative first derivative, and you can see there that we are decreasing along this interval here all the way up to -1. And as soon as we get to -1, from -1 to 0, it should be increasing. We saw that in our first derivative test. Then from 0 all the way to 2, everything along this interval here was also decreasing. That looks good. And then everything from 2 to positive infinity should be increasing again. And that looks good on this side of the graph now. So what this is eventually going to do for us is help us to sketch graphs without even needing access to a graphing calculator or Desmos. Right? Because now we know for sure where this graph is increasing, where it's decreasing, and eventually we'll be able to actually find those min and max values so that we can put those points on the graph, and then we'll basically have everything we need to sketch the graph. Any questions on that now? All right. So first derivative test. So we're going to suppose here that C is some critical number of a continuous function. If f prime changes from a positive to a negative at that value, then f has a local maximum at C. If f changes from negative to positive, then it's going to have a local minimum. And if it doesn't change at all, then there's no max or min. Okay. So again, it is possible that it goes from increasing to increasing around a critical number. Right? It's possible that it stays decreasing to decreasing around a critical number. But if it switches, then we either have a max or a min. And the way we determine that is whether it goes from positive to negative or from negative to positive. So we'll go back to the example we just did. Actually, I think that's the one we're going to do next. It is. Okay. So let's find the local min and max values for this function now. So what I'm going to do is I'm going to copy that number line that we already had because we've already found our critical numbers. We know where it's increasing, decreasing. Now we just want to find the min and maxes. Okay, so in this case, we had negative, make sure I have the right values. -1 was here, 0, and 2. This interval was negative. This one was positive. This was negative. This was positive. So again, what this told us was along this first interval, we were decreasing, then we were increasing, then it was decreasing again, and then it was increasing up here. So let's think about each of our critical numbers and what's actually going on there. At -1, the graph goes from decreasing to increasing because the first derivative goes from negative to positive. So are we going to have a min, a max, or neither at that point? That's going to give us a minimum, right? If it goes from decreasing to increasing, this should be a minimum. Now let's look at 0. This time it goes from positive to negative, increasing to decreasing. What are we going to have at 0 then? That's going to be a maximum. Okay, and then at 2, we go from negative to positive, decreasing to increasing. That's going to give us what? That's going to be another minimum. Now, in this case, they're asking for the actual max and min values. So what are we going to have to do then? So if we know those critical numbers and we know if they're mins or maxes, we actually have to plug those values back into the original function now to find the function values at those points. Okay, so I'm going to start with my -1. We're going to find f of -1. Again, make sure you're plugging into the original function, not the derivative here. This is going to be 3 times negative 1 to the 4th minus 4 times negative 1 cubed minus 12 times negative 1 squared plus 5. And at that point, you can just use a calculator if you want to. In this case, it's a negative 1 that we're plugging in, not too bad. This is going to be 3 times positive 1 minus 4 times negative 1 minus 12 times positive 1 plus 5. 3 plus 4 minus 12 plus 5 should give us what? Zero, right? Okay, so this should work out to 0. And again, we know for sure that this is a minimum. So once we get all of our values, then we'll come back and classify them as either local or absolute. Okay, but we don't know that for sure until we've tested all of them. All right, so now we're going to do 0. We'll do f of 0 here. 3 times 0 to the 4th minus 4 times 0 to the 3rd minus 12 times 0 squared plus 5. What's that going to equal? 5, right? Everything else just becomes a 0 here. Okay, so this one's pretty easy. That one should just be 5. All right, and the last one we need to test is 2. So f of 2. Again, if you just want to go to your calculator and put this in there, feel free to do that. And let me know what you get. Good, negative 27 is correct. All right, now, since these things are critical numbers, we know for sure if it switches that we're definitely going to have locals there, right? So each of these is at least a local min or a local max, okay, because they're going to be turning points. The only other question is, are any of them also an absolute max or min value, okay? So based off what we saw on the graph, right, and if you think about it, you can really just look at this first term here. We have an x to the 4th, which means both ends, if you remember end behavior from pre-cal, both ends are going in the same direction. The positive tells us they're both going up. Okay, so we know this thing's going to positive infinity. There's not going to be an absolute maximum, right? But this value down here at negative 27, even though it's a turning point, it's also going to be the absolute lowest value of your graph since the ends are going towards positive infinity. So we can classify this one as both a local and an absolute minimum. The other two, though, are still just going to be locals. So this one right here we said is a local, 0 was a max. And then this one up here is going to be a local, and at negative 1 we said that one was going to be a minimum. Okay, so 0 is a local minimum value. 5 is a local maximum value, and then negative 27 is both a local and an absolute minimum value for your graph. Any questions about how we got that? And again, at this point, now you could actually get a very accurate representation of what this graph would look like without needing access to a graphing calculator or Desmos, right? Because we know we're going to have a point at negative 1, 0. We're going to have a point at 0, 5. We're going to have a point at 2, negative 27. We know where it's increasing, decreasing. So as long as you understand the end behavior here is going towards positive infinity in both directions, then you've got exactly what you need to sketch this graph. Now, eventually, we're going to look at even more stuff, finding your intercepts and things like that to make it even more accurate. But even just from this information, you can get it pretty close. All right, example 3. You want to find the local max and min values of this function. Notice we're only going to look at the interval from 0 to 2 pi, right? So not all real numbers here. Just in this case, it's going to be like one full period of this graph. And actually, I misspoke. This one's not going to be periodic because of the plus x. Okay, so it's just from 0 to 2 pi. All right, so what's our first step going to be if we want to find local max and min values? Got to find the derivative. Good, right? So go ahead and find g prime. So what is g prime of x going to be this time? Perfect, right? So derivative of x is 1. Derivative of 2 sine of x should give us 2 cosine x. So there's our first derivative. Now that we have the first derivative, what are we going to have to do next? Good. Set it equal to 0 so we can find those critical numbers. So we have 0 equals 1 plus 2 cosine x. How are we going to solve that? Good. Subtract your 1. So we have negative 1 equals 2 cosine x. Divide by your 2. Now we have negative 1/2 equals cosine x. And at that point, we can do what? So cosine x equals negative 1/2. Good. We need to do the inverse cosine or arc cosine of negative 1/2 now. Right, so what is the arc cosine of negative 1/2 going to give us? Okay, good. Right. So remember, negative cosine means we're in quadrants 2 or 3, right? Because positives will be in 1 and 4. So in this case, this is going to be 2 pi over 3. Is there anywhere else where the cosine would be negative 1/2? Good. Third quadrant, that will be 4 pi over 3. So those are our two critical numbers this time, 2 pi over 3 and 4 pi over 3. Notice we don't need like plus 2 pi k or anything like that because we're only looking at the interval from 0 to 2 pi. Okay, so those are going to be the only two places where this is going to happen. All right. Now that we have our critical numbers, what are we going to do next? Good. Now we can do our number line test. Okay, so I'm going to draw my number line here. Now, since we're only going from 0 to 2 pi, I'm going to make sure that my number line starts at 0, ends at 2 pi. So I'm not putting arrows on the end, right? Because we only want to be between those two values. Then I'm going to put my two critical numbers on here. So we're going to have 2 pi over 3 and 4 pi over 3. The reason I do that is so that I don't accidentally choose values that are outside of the 0 to 2 pi. So when we choose our values now, the first interval is somewhere between 0 and 2 pi over 3. Next interval somewhere between 2 pi over 3 and 4 pi over 3. And then finally something between 4 pi over 3 and 2 pi. Okay, so what do you want to use in that very first interval then? Pi over 3 is perfect. All right, so let's do pi over 3. Again, this number line represents our first derivative, so make sure you're substituting into the first derivative to figure out is it positive or negative. So we're going to say f prime of pi over 3. I'm just going to come back up to here, right? Because it's going to be 1 plus 2 cosine pi over 3. What is the cosine at pi over 3? Should be 1/2. Good. So this is 1 plus 2 times positive 1/2. That's just 1 plus 1, which is going to give us what? 2. Again, all we really care about, though, is the sign, right? So is this one going to be positive or negative? It's going to be a positive, right? So everything in this interval here from 0 to 2 pi over 3 should give us a positive. All right, now we need something between 2 pi over 3 and 4 pi over 3. Pi is perfect, right? So 3 pi over 3 would be right in between. That's going to be pi. So we'll do f prime of pi. So 1 plus 2 cosine pi. What's the cosine at pi? I mean, -1. Good. Right, so remember that point is -1, 0. Cosine is the x value. We've got -1. If we do 1 plus 2 times -1, what's that going to give us? It's going to be a -1. Again, all we care about is the sign here. So this is actually just going to be a negative. Perfect. And finally, we need something in that last interval. What can we use there? 5 pi over 3 is good. F of 5 pi over 3. 1 plus 2 cosine pi, 5 pi over 3. What's cosine at 5 pi over 3? It's 1/2 again, right? Because we're back in quadrant 4. Cosine is positive there. It's going to be the exact same value that we got at pi over 3. So this is just 1 plus 2 times 1/2. And just like before, that should just give us 2. Again, all we care about is the sign. So that's going to be a positive. Good. All right. Now that we've done all of that, what are we going to do next? Okay, good. Now we can look at our number line and figure out where we have maxes and mins, right? So let's look. The critical number 2 pi over 3, is that going to be a max, a min, or neither? It goes from increasing to decreasing, right? Because it goes from positive to negative, which means there's going to be a maximum at that point. All right, then at 4 pi over 3, we're going to have a what? Good. That one goes from negative to positive. That's decreasing to increasing. That means this point is going to be a minimum. Any questions about how we determine that? All right, now, still one more thing to do because we need to know the actual max and min values now. So what's our last step? Good. Now we have to plug in those critical numbers into the original function to figure out what the actual values are there. So in this case, I'm actually going to do that right up here at the top. So we've got g of 2 pi over 3. So when we substitute that in, that's going to be 2 pi over 3 plus 2 times the sine of 2 pi over 3. What's our sine at 2 pi over 3 going to give us? Good. That's going to be square root of 3 over 2, and it is going to be positive because we're in the second quadrant. So 2 pi over 3 plus 2 times the square root of 3 over 2. And in this case, the 2's are going to cancel out when we do that multiplication there. So this is just 2 pi over 3 plus square root of 3. We already said that's going to be a maximum. In this case, it's just going to be, all we can really say is it's local, right? If you wanted to test the endpoints to figure out if it's also absolute, you could. We're only looking for local max and min, so we don't have to do that. Okay, this one right here is going to be a local maximum. All right, now we have the 4 pi over 3. We already said it's a minimum, so let's find that value. So we'll have g of 4 pi over 3. It's going to give us 4 pi over 3 plus 2 times the sine of 4 pi over 3. And what's our sine at 4 pi over 3 going to be? Good. Now we have 2 times negative square root of 3 over 2. Again, the 2's are going to cancel. This time it's just going to be a negative. So we're going to have 4 pi over 3 minus the square root of 3. And again, this is going to be a local minimum value. Okay. And that's it. Okay, so those are the two things we were looking for, local max and min values. There's our answers. Now, keep in mind, right, if WebAssign asks you round to so many decimal places, obviously you can put that in your calculator, get a decimal, and just put that in there. But if it doesn't specify, it does want an exact value. So those are the values that we'll be looking for in those cases. Okay. All right. So confused about how we got the critical points, 2 pi. So Hyro, right down here where we actually got those x values. Is that where you're looking? Okay, so when we take the inverse cosine of a value, we're looking for what angle would give us that cosine value. So this really goes back to trig and just thinking about your unit circle. So we're thinking in this case, where do we have a cosine value that's equal to 1/2? We know the cosine is the x value, so we just got to think about where on the unit circle the x value would be equal to positive 1/2. Well, that's going to be right up here and right down here. Right? That's where the x values would be positive 1/2. And those radian measures at those points now, oh, sorry, that should be negative 1/2. I apologize. I misread that. So we want it to be a negative 1/2 instead, which means we're actually over here and down here now. Okay. So cosine is always going to be negative in the second and third quadrants. And so this is actually going to be 2 pi over 3 is the radian value for that point. And then 4 pi over 3 is the radian value for that point. So it really does just come back to understanding the unit circle and how we find inverse trig values from the unit circle now. Okay. Any other questions on this one? But again, in general, right, whenever you're asked to find increasing, decreasing, or max and min values, first step, find your derivative, set it equal to 0, do your number line test to figure out where it's positive and negative. If you're asked for those increasing and decreasing intervals, then actually list out the intervals. In this case, we just wanted to know the maxes and min, so we didn't have to do that. We just want to figure out where does it switch from increasing to decreasing or vice versa. That's going to tell us where those max and mins occur. All right. Now, the next thing we're going to look at, actually, let's take our break. This is a perfect place to do that. So we'll say 11:10. We'll get started back up and we'll talk about concavity. All right. So, concavity. If a graph lies above all of the tangent lines on an interval, then we call the graph concave up on that interval. And if the graph lies below all of its tangent lines on that interval, then we say it's concave down. Okay, so basically, if you look at this graph at the bottom, it's probably easier to explain what concavity actually is just by looking at this. So notice from A to B along the bottom here, this is going to be what we call concave down. And again, the reason technically is because if I were to put tangent lines along this part of my graph, all of those tangent lines would lie above the curve at those points. Now, from B to C, we would say that this piece of our graph now is going to be concave up. And again, the technical reason for that is because if I were to put tangent lines on here, all of our tangent lines would actually fall below the curve. Okay. Then from C to D, it goes back to concave down again, because all of those tangent lines would then be above the curve. D to E is now concave up again. Notice here from E to P is also going to be concave up. And then when we get from P to Q, then it becomes concave down. Now, the one place where I have kind of a general rule of thumb, which helps me to understand, which way is concave up and down. The one place it doesn't work is at P, and I'll tell you why. I kind of think about, if you were pouring water onto this graph, right? Where would the water actually kind of, collect itself, and where would it just run off? And so like from A to B, obviously, if I pour water on that, it's going to run down, right? So that's concave down. Whereas if I put it in there from B to C, it's going to collect the water. That part's concave up. It's like a cup there, right? Then again, from C to D, if I pour the water there, it's just going to run off on that interval. From D to E, obviously it's going to pool in there. The hard part is seeing from like E to Q here, it switches from concave up to concave down, because obviously at P, it's not going to collect the water there. Okay, so those are the hard places to kind of see. But in general, right, it's again, wherever the tangent lines are above the curve is concave down. Wherever the tangent lines are below the curve, it's going to be concave up. Okay, that's the formal definition of this. Any questions about the concavity on that graph now? All right. So our test for concavity is actually going to be using the second derivative. If the second derivative is greater than 0 for all the x's in that interval, then the graph is going to be concave up on that interval. And if the second derivative is negative for all of our x's in an interval, then it's going to be concave down. So just like we were able to do a first derivative test to figure out where it's increasing, decreasing, now we can find our second derivative, do our number line test to figure out where it's positive and negative, and that's going to tell us where it's concave up and concave down. All right, now, here we've got a graph, right? It tells us the population for Cyprian honeybees raised in an apiary. So we've got this graph down here shows us time in weeks along the horizontal axis, and then the number of bees in thousands of bees along the vertical axis. We want to know, how does the rate of population increase change over time? Okay, so what you're trying to think about right now is the rate of increase in your population. How is that changing over time? So let's start at the beginning of our graph. So at 0, 0, as we go along, how is that rate of increase? Is it slow or fast at the start of that graph? It's a slow rate of increase, right? So our population not growing very fast in those first weeks, right? Then what happens to our population increase? It becomes faster, right? It speeds up. So that rate of increase in population gets faster. And if you think about it, it's a rate of increase that's becoming faster. That's like a slope of a tangent line, right? So our first derivatives are becoming larger. That's why it's growing faster. Then as we get towards the end of the graph, what happens? Okay, good. So be careful in using the word decrease, right? Because that's technically saying that the graph itself is decreasing. What happens to the rate of population increase? It starts to even out, it slows down again, right? So the rate at which the population is increasing slows back down, similar to what it was at the beginning of the graph. Okay, so we start out with a slow rate of population increase, then it speeds up, and then that rate of increase slows back down again. But at all points, it's always increasing in population, right? Just the rate at which it's increasing is what's changing there. Any questions about that? All right, so if you had to choose a point in time where the rate is the highest, where would you say that happens approximately? All right, so at 1870, right, so you're looking at this very last point, that's the highest population, right? But where is the population increasing the fastest? Right? Where is that rate the highest? Yeah, somewhere in the middle of the graph, right? So probably right in here, because that's where the slope of our tangent lines would be the steepest for our graph, and that's where that rate of increase is the fastest. So whenever it's saying when is the rate the highest, you're really thinking about where is the steepest part of that graph. That's what matters in this case. So I'd say somewhere around 12 weeks, right? And since it's asking for when, right, we're looking for the time. All right, now the last question is over what interval is P going to be concave up and concave down? All right, so now we want to think about our actual concavity. We're going to list out the interval or intervals where it's concave up and concave down. So let's think about concave up. Are there any intervals on this graph that would be concave up? Good. Everywhere from 0 to 12 now, if I were to put tangent lines on there, the slopes of the tangent lines would be below the graph, right? So everywhere from 0 to 12 is going to be concave up. What about concave down then? Again, concave down means the tangent lines would be above the curve. So where would our tangent lines be above? Everywhere from 12 to 18. Good. So that's the entire domain of the function now, right? Because we're stopping at 18 weeks. Okay, so from 12 to 18, that would be concave down. Any questions about identifying concave up and concave down given the graph now? And just to kind of, tie this back into what we just said, we know the second derivative is what we're testing. Well, the second derivative gives us rates of change of rates of change. So if you look at this graph right now, we're basically saying, well, whenever that rate of change of the rate of change is positive, whenever it's increasing, then we know it's going to be concave up. And whenever that rate of change slows down, becomes negative, that's where it's going to actually become concave down, right? And so that's why at 12, it actually switches, because that's the highest rate of change we have. That's where the slopes of our tangent lines are the steepest. And then after that, they become less steep. And before that, they're already less steep. And so that's why we change concavity at that point. Any questions on this one now? All right, now, before we go to the next slide, I'm going to tell you on this graph, this point at 12, this is what we call an inflection point. Okay, so anytime you have a point on your graph where the concavity switches from either concave up to concave down or concave down to concave up, then we say there's an inflection point at that point. That's the definition on the next slide, but I just wanted to show you on this graph, we actually do have one, right? And that's where it switches concavity. Okay, so the point P on the curve is called an inflection point. As long as F is continuous there and the curve changes from either concave up to concave down or concave down to concave up. So again, just like we can find mins and maxes using our number line test and seeing where that first derivative goes from positive to negative, now we can find inflection points because we'll do our second derivative, do our number line, figure out where it goes from positive to negative or negative to positive, and anywhere where it switches, then we know there's an inflection point there. All right, example 5. We want to sketch a possible graph of a function that would satisfy all of these conditions. There will be a question on the test like this, okay? So I like this question because it's the only time I'll ever ask you to graph anything, because otherwise, if I just give you a function, I know you can put it in Desmos and get a graph, right? But if I just give you something like this and ask you to graph it, there's no way to put this in Desmos. You have to understand what all this stuff tells you to be able to sketch this graph now, okay? So let's start out, and we're just going to go piece by piece, figure out what each piece tells us about the graph, and then we're going to try to sketch it. So starting here with f of 0 equals 0, what does that tell us about our graph? Good, right? There's a point at the origin, right? There's a point at 0, 0. So I know for sure on my graph, I need to put a point at 0, 0. That's what that tells us. All right, what about f of 2 equals 3 then? There's going to be a point at 2, 3, right? So I know 2, 3, also going to be a point on my graph. And then f of 4 equals 6. It's going to be a point at 4, 6. Good. So if we're sketching, first thing I'm going to do, I'm going to go ahead and put those 3 points on my graph. So I know I've got one at the origin, 0, 0. I've got another point at 2, 3. So go over 2, up 3. Here's another point. And then I'm going to have a third point at 4, 6. Here's 4, 4, 5, 6. Here's my third point. Okay. And so this is how I would actually do a problem like this if you see it on test, right? Just go through, find what you know, and go ahead and start putting it on the graph. All right. Now, the next piece here says that f prime of 0 is equal to f prime of 4, and they're both equal to 0. What does that tell us about our graph? So if f prime of 0 equals 0 and f prime of 4 equals 0, what do we know? So the points where your derivative is equal to 0 are called what? Critical points, right? So these are the critical points or critical numbers of your graph now. So we know we have critical numbers at 0 and 4. We don't know for sure if they're mins or maxes, right? But we know their derivatives are equal to 0, so we know for sure that they are critical points. Okay, so keep that in mind. Chances are there could be turning points there. There could be mins or maxes there. That's what we're going to look for. All right, so that takes care of the first line. Now let's look at the second part. This says that f prime of x is greater than 0 for 0 less than x less than 4. What does that tell us? The first derivative is greater than 0 for all the x values between 0 and 4. What do we know about our graph? Okay, so f prime of x is positive if it's greater than 0. So if the first derivative is positive for all the x values from 0 to 4, what do we know about the graph? So it doesn't tell us concavity, right? What does the first derivative being positive tell us? The second derivative tells us concavity. First derivative tells us, okay, so it is going to help us with local min and max, right? But before that, even, if the first derivative is positive on an interval, what do we know about the graph? Think about your number line test with the first derivative. It's increasing, right? So we know in this case that our graph is going to be increasing on the interval from 0 to 4. That's what that tells us. Now, if we find out that it switches to decreasing somewhere, then yes, we know there's a maximum there, right? But for right now, all that tells us the first derivative is positive from 0 to 4. That means the graph is going to be increasing from 0 to 4. Any questions about that? All right. Now, the next piece says that f prime of x is less than 0 for x less than 0 and x greater than 4. What does that tell us now? It's going to be decreasing on those intervals, right? Because the derivative is less than 0. And so what are those two intervals going to be? Okay, first one's negative infinity to 0. Good. And then also what? 4 to infinity. Perfect. So everything less than 0, everything greater than 4, the first derivative is less than 0, meaning it's negative. Therefore, on those two intervals, it should be decreasing. All right, now before we try to put that on there, right, because basically at this point we know it's decreasing all the way to 0, it's increasing from 0 to 4, and then it's going to be decreasing again from 4 to infinity. Okay, so we've got a decent idea right now of what this is going to look like. Before we do anything, though, let's go ahead and look at this last line and figure out what these second derivatives tell us. So f double prime of x is greater than 0 for x less than 2. What do we know? Good. If the second derivative is positive, it's going to be concave up. So it's going to be concave up. And what is that interval going to look like? Good. So be careful here, right? It just says x is less than 2. Okay, so that means that it's going to be what? So if x is less than 2, where would that start? At negative infinity, right? So we got to go all the way from negative infinity to 2, right? That whole interval now is going to be concave up. And then the last piece says that f double prime is less than 0 everywhere that x is greater than 2. So what does that tell us? Good. This is going to be a concave down interval because our second derivative is negative, and that's going to be everywhere that we're greater than 2, so from 2 to positive infinity now. So we just have to make sure that when we sketch this now, our concavity is going to switch, which means what can we say about the point at 2 then? It's an inflection point. Good. So we also know because our concavity switches at 2, there's going to be an inflection point at x equals 2. All right. Now, we can also go back and think about mins and maxes just to make sure that as we're sketching that we end up with what we want there. So do we have any points where we're going to have a min or a max? Think about those increasing and decreasing intervals. We know wherever it switches from increasing to decreasing or vice versa, we're going to have a min or a max there. All right, good. The points at 0 and 4, that's where it switches. So we know there's going to be a min and max at those points, right? So let's think about which one's a min and which one's a max. Okay, so if we go from negative infinity to 0, it's decreasing. Then it switches to increasing from 0 to 4. So at 0, we're going to have a what? That's going to be a minimum, right? So x equals 0 should be a minimum there. And then it goes from increasing at 4 to decreasing at 4. And so there we're going to actually have a maximum. So the critical numbers will tell you where they are, right? So the 0 and the 4. But then you're going to actually have to think about where it switches from increasing to decreasing to make sure you know which one is which, right? Because in this case, it goes from decreasing to increasing at 0 and from increasing to decreasing at 4. That's how I know which one's a max and which one's a min now. Okay, but yes, the critical numbers tell you where it should be, right? But then you got to look for the increasing, decreasing to figure out what they actually are. Any questions about just labeling all of that information now? I would say on a test, do exactly this, right? Because even if your graph is wrong, I can still give you partial credit for listing out all the stuff that you know. Okay, so find those increasing and decreasing intervals. Tell me where it's concave up and down. If you notice any mins or maxes or any points of inflection, label those, right? Because I can at least give you the partial credit for knowing all of that, even if the graph doesn't look right. All right, now let's see if we can put it all together and graph it. Okay, so starting from negative infinity on the left-hand side of our graph, what's the left-hand side of this graph going to look like? What do we know about it? Okay, so be careful. From negative infinity to 0, the left-hand side of the graph is actually doing what? decreasing. So everything over here on the left-hand side of the graph is going to be decreasing all the way until we get to 0, because at 0 we have a minimum, and that's where it switches to increasing, right? Okay, so make sure it's decreasing until we get to 0. Then from 0 to 4, everything in between there is increasing. But we also know that we have this point of inflection at 2, meaning that it's going to switch from being concave up to being concave down at that point. So make sure you're not making this a straight line between all three of these points. It needs to increase, but when we get to that point, the rate at which it increases needs to slow down so that we get a point of inflection there. So there it switches from being concave up to being concave down, even though it's increasing along that entire interval now. Right. Then we have our maximum at 4, and then it starts to decrease again from 4 to infinity. And so then the other side of the graph is just going to look like this now. Any questions about how we got that graph? Again, once you sketch it, just kind of go back, make sure all your stuff makes sense. We have the points labeled. That was the first thing we put on there. We're decreasing from negative infinity to 0. We're increasing from 0 to 4. We're decreasing from 4 to infinity. We have to be concave up from negative infinity to 2. And then we need to be concave down from 2 to infinity. That looks good. That means our concavity switches at that point 2. That's our point of inflection. And we have a minimum at 0 and a maximum at 4 now. And there are some more problems in the book similar to this. So if you want to look at those exercises, along with there's homework problems, right, where you're matching graphs. But if you're actually just trying to sketch it, by yourself, I would take a look at the exercises there, because again, there will be one similar to this on the test for sure. All right, so our second derivative test now, again, suppose that f double prime is continuous near that c value. If f prime of c is 0 and f double prime of c is greater than 0, meaning it's positive, then there's going to be a local min there. And on the other hand, if f prime of c is 0, but the f double prime is less than 0, meaning it's negative, then there's going to be a local maximum. Now, what this does for us is basically says, well, if c is a critical number, right, if the derivative is equal to 0, and we know that we have concave up on our graph, then it has to be a min, right? Because the only way that c could be a critical number, right, that the derivative could be equal to 0, and the graph be concave up at the same time, is if this is a minimum. Okay, so f double prime of c is positive, meaning it's concave up, and c is a critical number, then we have a min. And on the other hand, if our c value looks like this, f double prime of c is negative, but c is still a critical number, then we're going to have a maximum. Okay, so this is just another way to test for mins and maxes now, without even having to do the increasing decreasing test. If you do your second derivative test instead and know where it's concave up and down, but still know what your critical numbers are, we can still find mins and maxes this way. Now, in general, usually you're going to be finding increasing and decreasing along with concavity anyway, so you're already going to know your mins and maxes. Okay, so it's up to you how you want to find those, but this is just another way to do it. Any questions there? All right. So we want to discuss the curve with respect to concavity, points of inflection, local min and maxes, and then it says use it to sketch. What we're going to do at that point is we'll just look at Desmos to make sure that all of our information is accurate. Okay, but I want to make sure we can find all of this stuff. All right. So what do you think we need to do first in this case if those are the things we're looking for? Find your first derivative, right? So we got to find y prime. So what's y prime going to be this time? And just for the sake of time, I'm going to go ahead and write it out because I think we can all do it. Power rule 4x cubed minus 12x squared, right? Now, once we have that derivative, though, what are we going to do with it? Good. Set it equal to 0. Find those critical numbers. Now, once we set it equal to 0, what are we going to need to do with the right-hand side? Got a factor. Good. So we have a common factor of 4. Actually, 4x squared is a common factor here, right? So I'm going to go ahead and take out that whole thing, 4x squared. That should leave us here with just x minus 3. All right, now that we have our factors, then we can do what? Set each factor equal to 0. 4x squared is 0. X minus 3 is 0. So our two critical numbers are going to be what this time? Good, just 0 and 3, right? Divide by 4, take the square root, that's still 0. Add 3, that gives you 3. All right, now we have our critical numbers. Now we can do what? Number line, perfect. Okay, so I'm gonna do my number line. This one is our f prime or y prime, first derivative number line. We have 0, we have 3. All right, so now we need some test points. What do you want to test in that first interval? -1, okay. So again, we're plugging that back into the first derivative. Wherever you want is fine, right? You could do it in that very top line. You could do it in the factored form. I typically go with the factored form since I know I'm only looking for signs anyway. This is 4 times -1 squared times -1 minus 3. 4 times -1 squared is going to be what? That's going to be positive 4, right? So that's a positive. -1 minus 3 is going to be what? A negative. And a positive times a negative should give us a negative. So everything down here now should be negative. All right, now I'm going to do something between 0 and 3. What can we test there? Positive 1 works. And 4 times 1 squared, 1 minus 3. So 4 times 1 squared, is that going to be positive or negative? Be positive. 1 minus 3, positive or negative? That's going to be negative. Positive times negative is negative. Good. Now notice here, this is one of those cases where it does not switch, right? We have back-to-back negatives here, and that's why it's so important to always test. All right, then we need something bigger than 3. 4 works. We have 4 times 4 squared, 4 minus 3. 4 times 4 squared is positive. 4 minus 3 also positive. So that should be what? Positive overall. Good. All right, now that we have that, okay, we know one thing we're looking for are any local maxima and minima, right? So we're looking for max and min values. What can I do now to find those? Or do we even have any? That would be another question, right? Because it could be possible that we don't have any at all. Do we have any mins or maxes? Okay, good. The only place we're going to have one is at 3, because that's the only place it switches from negative to positive, right? Or positive to negative. That's the only place. So is that going to be minimum or a maximum at 3 then? It is going to be a min. Good. It goes from negative to positive. That means decreasing to increasing. Therefore, there's going to be a minimum there. If you want to know the actual value, you could plug it in, right? But I'm not going to do that here just for the sake of time. We know there's a local min at x equals 3 now. Any questions about finding local max and min values? Again, 0 is a critical number, right? But there is no local min or max there because it does not switch from negative to positive or vice versa. All right, so now we've got local min and maxes. Now we want to think about concavity. So what are we going to have to do next? Second derivative, good. Come up here, find my second derivative. I'm working off that first line for my first derivative, so I can just use my power rule again. So this is going to be 12x squared minus 24x. So now what do we have to do? Good, set that one equal to 0, which means we need to factor again. Here we have a common factor of 12x, so I'll take that out. Leaves us with x minus 2. Right, then we can set each factor equal to 0 just like we did with our first derivative. So 12x equals 0. X minus 2 equals 0. Good. That means we're going to get x equals 0 and x equals 2. Now we do our number line test. This time, this is the second derivative. Just make sure you're plugging into the right place when you do your test. So what value do you want to test first? Negative 1's good. Okay, so we'll do 12 times negative 1, negative 1 minus 2. Okay, this is going to give us a negative times a negative, which is going to be what? Positive. Good. So everything down here should be a positive. What value do you want to test between 0 and 2? Positive 1. So now we have 12 times 1 times 1 minus 2. 12 times 1 is positive. 1 minus 2 is negative. Overall, that's what? Negative. Good. And then finally, we need something bigger than 2. 3 is good. So now we have 12 times 3. 3 minus 2. 12 times 3 is positive. 3 minus 2 is also positive. So overall, it's going to be positive. Perfect. Any questions about the number line there? All right, so now we just need to know where is it concave up, where is it concave down. So what are the interval or intervals where it would be concave up? Okay, negative infinity to 0 is the first one. Good. Anywhere else? Also 2 to infinity. Good. Both of those are positive. Those will be our 2 concave up intervals, which means the only place that it's concave down is going to be the interval from 0 to 2 then. All right, now, do we have any inflection points this time? All right, so 2 goes from concave down to concave up. It switches from negative to positive there. So at x equals 2, we would have an inflection point. Do we have any other inflection points? 0 is also, right, because it goes from positive to negative there. We're also going to have a point of inflection at x equals 0. And again, if you wanted to know the actual points, you could plug those x values in, get the corresponding y values, and that would tell you the actual ordered pairs if you needed it. Okay? All right, so we're out of time, but that's how you do a problem like that. Again, there will probably be something similar to that on the actual test where I kind of say, find all the important stuff, right? Increasing, decreasing, mins and maxes, concavity, and points of inflection. You just have to know to find your first derivative and second derivative, set them equal to 0, do your number line test to find all that information. Okay? All right. That's everything for section 3.3. Again, the 3.1 to 3.3 homework's due by midnight tomorrow night. Make sure you're working on that. Let me know as you have questions. Otherwise, have a great afternoon, and I will see you all tomorrow.